Alright, for the next example, we are going to require the use of a calculator of some sort, so please make sure to have one handy for this one. We are going to estimate the area that is found under the curve y equals the natural log of x in between x equals 1 and x equals 3, and we are going to use n equals 5. So, with that in mind, first thing I want to do is just give you a little visual of the approximation that we're about to make here. So natural log of x looks approximately like this. It does have an x-intercept over here at x equals 1, and x equals 3 is just slightly to the right of that. So the area that we're going to try to find is going to be in this general region right here. Now to break this up into 5 intervals, we're going to be inserting 4 additional endpoints inside the interval to give us a total of 5 intervals. So with n equals 5, first thing we'll do is calculate what is the value of delta x. So delta x is defined as b minus a over n, where b and a are referring to the endpoints for your interval. That'll be 3 minus 1 all over 5. And because I don't feel like going fancy fractions with this one, we'll just stick with a decimal and call that 0.4. So starting at x equals 1, we'll be increasing by 0.4 at a time until we get up to x equals 3. So what I'd like to do is start with the left-hand approximation. And once we do something similar to what we did in the last example, I'll show you how we can shorten this process a bit. So the intervals with which we will be concerned, we're starting at 1 and increasing by 0.4 at a time. So the first interval will go from 1 to 1.4. Next interval, 1.4 to 0.4 larger than that, that'll be 1.8. Then we'll go from 1.8 to 0.4 larger than that, that'll be 2.2. Then that'll be 2.2 to 0.4 larger than that, 2.6. And finally 2.6 to 0.4 greater than that, and that'll be 3, giving us our right endpoint for the interval. So for the left-hand approximation, the representative point that we'll be using, which we refer to as x sub I star, will be the left endpoint of each interval. So it'll be 1, 1.4, 1.8, 2.2, and 2.6. We will also need the height of the approximating rectangle for each of those, and the height is going to be what we get by evaluating f of each of these. Now the function in this case is the natural log of x, so we'll be taking the natural log of each of these values. Rather than simplifying at this step, what I'd like to do is leave it unsimplified with the knowledge that we're just going to toss all of this into the calculator after we're done. So that gives the heights of the rectangles. For the areas of the rectangles, we'll be taking those heights and multiplying them by the corresponding length of the base. The length of the base is going to be 0.4. So we'll be doing 0.4 times the natural log of 1, 0.4 times the natural log of 1.4, 0.4 times the natural log of 1.8, 0.4 times the natural log of 2.2, and 0.4 times the natural log of 3. Extra set of, 2.6. 2.6. Got ahead of myself. Now there is a slightly more succinct way that we could say all of this. What we're supposed to do is take all of those areas and add them all together. But if we add them all together, they all have this delta x in common. So what we could do is simply factor out that 0.4 and then add all of those natural logs together. So natural log of 1 plus the natural log of 1.4 plus the natural log of 1.8 plus the natural log of 2.2 plus the natural log of 2.6. Tossing that all into a calculator will give us the left-hand approximation for our area. So with that in mind, I'm going to grab my graphing calculator and do exactly what I just said. 0.4 times parentheses natural log of 1 plus natural log of 1.4 plus natural log of 1.8 plus the natural log of 2.2 plus the natural log of 2.6. We'll also round that off to a reasonable number of decimal places. Let's go for 4 decimal places. So 1.067 with a 29, we'll round that up to 3. Now it's for this purpose, we can also shorthand what we're going to do for the right-hand approximation, because quite literally the only thing that's going to change for the right-hand approximation is the representative point that we're using. So as far as the right-hand approximation is concerned, if we were to do something similar, rather than using the left endpoints for each interval, we'll use the right endpoints for each interval. So natural log of 1.4 plus the natural log of 1.8 plus the natural log of 2.2 plus the natural log of 2.6 plus the natural log of 3. And once again, we can approximate that. So again, tossing this all into the graphing calculator, that'll be 0.4 times natural log of 1.4 plus natural log 1.8 plus natural log 2.2 plus natural log 2.6 plus the natural log of 3. Rounding that off at the 4th decimal place, that'll be 1.5067. Now a better approximation for the area is going to be the average of these two values. So we'll take the left-hand approximation plus the right-hand approximation and divide that by 2. For that, once again, I will be turning to the graphing calculator. That'll be 1.0673 plus 1.5067, and then we'll divide that by 2. So the average of our two approximations is going to be 1.2870. Now that'll be the better approximation than the left-hand or right-hand. I can tell you that the left-hand approximation was an under approximation and the right-hand approximation was an over approximation. Since we haven't done one of these yet, let's also do a midpoint approximation. For the midpoint approximation, we will need the midpoint of each of these intervals. So the midpoint is going to be the point that's halfway in between each of the two endpoints. The midpoint of 1 and 1.4 would be 1.2. And then because our delta x is 0.4, we can simply add 0.4 to that until we get all 5 of our heights that we need. 2.8 would be the last one. Now, of all of the approximations, we can prove using some calculus that the midpoint approximation is going to be the best approximation of all of these. So 0.4 times natural log 1.2 plus natural log 1.6 plus the natural log of 2 plus the natural log of 2.4 plus the natural log of 2.8. You'll notice that this one is pretty close to the average of the left-hand approximation and the right-hand approximation. But in Calculus 2, specifically it's section 7.7 of our textbook, they actually prove why the midpoint approximation is the best approximation.